Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 194, I chat with Walther about Ultra D glasses-free 3D. So stay tuned.
Netcasts you love.
From people you trust. This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded February 13th, 2014. Episode 194, Ultra D Glasses-Free 3D. Hey there, Scott Wilkinson here, the Home Theater Geek and Director of Content at avsforum.com. This week's guest geek is Walther, the CEO of C-Cubic, a subsidiary of Stream TV Networks, the developers of Ultra D Glasses-Free 3D. And Walther is the primary inventor of this technology. Hey, Walther, welcome to the show.
Thank you for having me.
It's pretty late at night where you are. We're talking to you from your home in the Netherlands, so we've become quite the international show here today. Thanks so much for being here.
Yeah, it's 11:30 here, so I'm almost getting ready to go to bed.
Well, thanks so much for staying up with us for the next hour while we talk about Ultra D, which has been always very fascinating to me. Before we get into it, let me quickly just mention that those who are watching live on live.twit.tv or logged into the chat room at irc.twit.tv can post questions for Walther as we go along, and I'll pass along as many as I can. So let's start with the basics of how 3D vision works. I mean, all humans, most humans anyway, have two eyes, and we look out on the world and we see 3D. How exactly does that work from a perceptual point of view?
Just to start with, the film industry and TV has hijacked the term 3D and used it mostly in the last few years for stereoscopic, or as the stimuli is called, stereopsis. That's the only 3D perception thing that is addressed by glasses-based 3D, as is used in cinemas or in nowadays the television sets that are equipped with 3D, so to speak. That's why we had to flee to Ultra D, where the 10 or about 10 stimuli that are available for seeing 3D can all be addressed if necessary. So not only stereopsis, because then 10% of the world population wouldn't have use for that, because 10% of the population are hampered or are even stereo blind, so to speak. They see only with one eye. And with
so let's make sure we understand the terminology here. Stereopsis is the process of the stimulus of seeing through two eyes that are separated by some distance, and the brain interpreting the differences between those two views into a 3D image. Have I got that right?
That's absolutely correct, yes.
Okay, good. But there's more to 3D vision than just stereopsis, which is the only one that glasses-based 3D cinema and TVs actually use.
Exactly. The second in importance is motion parallax. So if we try to estimate the size of things at a bigger distance than 10 meters, let's say, so 30 feet, you have to rely on motion parallax, and to be able to see that, you wiggle your head a little, and then you can see the relation of size of things, but also how they move in respect to one another. And also from that, we perceive depth. And then we have perspective lines and depth from sharpness and some 10 stimuli that also help us to see 3D.
Okay, so motion parallax is when you move your head around and you can sort of see if one object is in front of another, you can see their relationship change. Sharpness at a distance Of course, our eyes adapt, right? I mean, if we look into the distance, we can see things sharply, and then things
Hmm.
close up look fuzzy, and vice versa, right? If we're focused on something close up, then the distance looks fuzzy. Is that what you're talking about there in terms of distance sharpness?
Yes, exactly.
Okay.
And filmmakers use that while they can make their camera sharp at a certain distance as well. They use that feature also to help people estimate the depth or the distance from things. Yes.
Mm-hmm. And that works even in 2D images, films, and television shows. I mean, the director or the cameraman will set that up in such a way with a long depth of field or a narrow depth of field, and in some cases that can sort of almost look like it's a 3D image, but it's also fixed. It can't be
Yeah.
changed. You're looking at it, and it's the same for everybody.
Yeah. Yeah. And so we have more of those. One of which is object or feature recognition. If you see my head now, you can almost estimate how big it is, and you can deduct the depth of that and the depth of the features from aspect ratios of, for instance, my eyes and my nose. So also from that, the one-eyed can see 3D aspects of a scene, but also from perspective lines. You see the rack behind me, you see perspective lines, and also from those we can see 3D. So there is a number of stimuli that helps us seeing 3D with one or two eyes, and the distance between the eyes doesn't help us if the distance becomes bigger than 10 to 15 meters, so 30 to 45 feet.
The distance between us and the object we're looking at.
Exactly.
So stereopsis doesn't even work past 30 feet or so.
Exactly. Yep.
So then we need to use these other stimuli to, continue to perceive in 3D.
Yep.
So as you said at the beginning, glasses-based 3D, which is really mostly what we're used to these days in movies and on TV at home, only use glasses. So you're only using the stereopsis, and if something appears to be farther than 30 feet away, it's not going to be very effective.
Exactly. Yeah. Then the disparity, as it is called, so the distance between the horizontal distance between the images that both eyes see is then too small in respect to the distance and the perspective, and from that you cannot derive 3D perception.
So it just looks flat.
It just looks flat. Exactly.
Yeah. Well, people have been trying to create glasses-free 3D for many years. It's also more technically called autostereoscopic, which is a display that can actually show you a 3D image without using glasses. I remember as a kid, seeing little toys with lenticular sort of film on top of an image, and this lenticular film actually felt kind of like it had grooves in it, and you could move it around and you could see sort of a 3D image, but it was pretty low res.
Yeah. What a lenticular does, and the lenticular cards of some time ago used the same principle as some of the autostereoscopic televisions or displays do, is they direct light coming from the card behind it in different directions. And if you then print the so-called views in vertical stripes on that card, the vertical stripes are seen from different directions, different stripes are seen. And if these stripes contain image information, then from a particular point you see one image, you move a little sideways, or you use your other eye, you see another image. If you can use both eyes, you then can see stereo if things are designed well. And if you move sideways or you rotate the card, you see motion parallax.
So, so I have seen early examples of auto stereo TVs, and generally speaking, they only have a very limited number of places where you can be, where you can put your head. to actually see the two images, the right eye in the right eye and the left eye image in the left eye, pardon me. And if you move around much, you get this weird wavy kind of sensation. And if you're in the wrong place, it doesn't look right at all. And typically there are only a few places that it looks right, maybe 7 or 9, usually an odd number, as I recall. And so that seems to me to be a big limitation.
It is, and it's a disadvantage of the technology. You use lenses, so you magnify the pixels in one direction at least, perpendicular to the lenticular, and you do that to be able to direct the light of the pixels or subpixels behind these lenses in a certain direction. This means that you can create views which are dependent on the direction from which you look at the screen. And your both eyes look from different directions to the screen. So you make sure that behind the lenses images appear that make sure that you have, at the optimal viewing distance, a stereo pair on your eyes. But if you want to do that over the whole hemisphere that is available in front of a display, you have to divide the resolution in all these stereo pairs of views, which, if you put it to the limit, lets you end up with no resolution at all. So manufacturers have chosen to limit the number of views. Mostly the barrier-based, as well as the lenticular screens, use something like 7 or 9 views. Philips used to do that as well with their lenticular solution. They made 9 views, an odd number, and they did that on purpose, while the views that are adjacent to each other have crosstalk. And if you now make sure that you have an odd number of views, you always have one view on your nose and one view on your left and on your right eye. And that makes sure that the 2 views that reach your eyes have no or hardly any crosstalk.
Right, which is something we certainly want to avoid, because if you see the left eye image in the right eye or vice versa, then it looks double or fuzzy and looks pretty disconcerting, I should say.
Yeah. That pseudostereoscopic images, if the left and right information, visual information is switched, it's called pseudoscopic. If you look long enough, you'll start to see 3D again, but your brain has to work very hard to achieve that. So most people get a headache from that.
Exactly.
Yeah.
So how did you, Ultra D, which is your auto stereo or glasses-free 3D system, overcomes many of these problems. Tell us about it, how it came about, how you decided to develop it, and how it ends up not causing these problems.
What we do is we don't try to generate complete images for a left and a right eye. We generate something based on the pixel information that is available that is something similar or analog to a light field, where light is directed through an optical system in front of the LCD or whatever system you use to generate the light emitting pixels. And it's the optics are positioned in such a way that by moving from left to right, you see multiple partial images or fractional images, which build a 3D perception. So it's not stereo pairs that you see as such, which are stereo pairs you see with normal lenticulars or with barrier type autostereoscopic systems. We have generated a system or developed a system that makes a lot of partial views to be seen as a complete 3D perception, where we also have stereopsis as well as motion parallax. So if you move sideways, you seem to look around objects and you see things appearing and disappearing behind someone or behind something.
That sounds almost like holography. Is this related to that?
It is. The idea comes from that. I studied physics when I was young, and I graduated or did my master's in holography. And this is a mix of diffractive, holographic optics, and refractive, the normal lens-based optics.
And yet you're not using lasers, so it's not holography in that sense. Holography depends upon using coherent light from a laser, but clearly LCD TVs and other kinds of TVs don't produce coherent light.
No, you're right. And holography is also strongly wavelength dependent. And the pixels in a TV tend not to emit just one wavelength. So we have to compensate for that as well. You have these true color holograms that you see printed on foil, which generate also on not coherent light a 3D image. You know these security stickers that you have on your credit card, things, these little holograms. They don't rely on coherent light. They can be seen in sunlight or on a bright artificial light. And that technology is used in our system as well.
Oh, okay. I should just quickly point out to anybody who might not know the term coherent light, it refers to when all of the light waves coming out of the laser are lined up, are aligned exactly, as opposed to sunlight or light coming from a light bulb or from a TV, where all the waves of light are not lined up. They're randomly aligned rather than specifically and exactly aligned as they are out of a laser. So that's what I'm just trying to make sure everybody understands what coherent light, what that means. Chumley in the chat room is saying, I'm left eye dominant. In fact, very left eye dominant. Does this have any effect on your system?
Obviously, you're a bit hampered in seeing 3D as people that have stereopsis. If you have, my daughter has a right dominant eye, so I really am I know about these things, and I've really looked for solutions of her problem. And she sees 3D with our technology almost as well as she sees 3D in real life. And the guy that asks the questions can probably confirm that he can see 3D, or at least 3D relations of object in his environment, despite the fact that he has one dominant eye.
And your technology allows people to see 3D on the screen, on the TV screen, because it uses things in addition to stereopsis, such as motion parallax.
Yeah, exactly.
So how can you explain in any more detail how you get this motion parallax out of your system, whereby you can actually look around an object and see the relationship between two objects on the screen, one of which is in front of the other, presumably. And you move your head around and you can actually see quote unquote around it like a hologram. I'm still not quite sure how you're able to do that.
For stereo, most of the footage is shot with a stereo pair of cameras.
Right.
The baseline of which can be exactly the baseline or the distance between two eyes. What most stereoscopic filmmakers do is make that baseline a little bigger, or even have a third camera, where the cameras look in respect to my head, something like this. So you can see from there where my map is at the wall to the cupboard on the right-hand side. The cameras can see that. I have that visual information in the footage, obviously, so I can show if people move around from this position to this position, all the information that is behind me. And we work with that information. We have called that occlusion data. It's now occluded by my head, but the map behind me can be seen if I move my head away, or if I had a camera looking from this position that could see behind my head. So we use that information to fill in the occluded information and to make it possible that people move in respect to what they see and then see appearing what's behind something. And the speed with which it then appears gives a good estimation in the brain for how far it is away.
Ah, okay, that makes sense. Tell us a little bit more about these partial views, though. I don't think I quite have a handle on that yet.
Now,
Um, that the two views, or the two, what the eye is, each eye is seeing, are partial views. You said earlier, not complete views.
exactly. If you look at a 2D screen, you look at a multiple partial images. In fact, every pixel is an image. It has only one color, but it makes one point at the screen different from the other.
Right.
All these pixels together are in our, and if the resolution is high enough, the number of pixels is high enough, are in our brain fused to see an image, which can contain lines or all sorts of forms, but all these forms are built out of pixels. If I, with my system, make 3D pixels, I could do exactly the same thing. Only I have more or less a virtual cloud of pixels, or I have a light field moving towards me, in which I can have partial information, let's say a volume resolution, in which I can move around, or at least I can move sideways, because we only support horizontal parallax, so that if the viewer holds his head upright, not if he lies down on the couch, and if he moves sideways, so not up and down. We don't have vertical parallax.
Is that a limitation of the optical system, or
It's a
what?
choice.
Ah,
If we normally we sit upright, we walk upright, and the eyes are beside each other.
horizontally,
Um,
yeah.
yes, and if you start lying on the couch and watch then TV, then our system doesn't work anymore. Nor does the glasses-based stereoscopic TV.
Well, certainly not the active glasses, but passive glasses in home TV use circular polarization. So wouldn't that still work if you were on your
It
side?
Yes, it would still work in the sense that it splits the images to go to the correct eye,
Uh-huh.
but the images were shot and reproduced on your television to be seen side by side.
Yeah.
And then you suddenly see them top bottom. And from that, we can't derive any 3D information anymore.
Yeah. Yeah. I remember when LG first came out with passive glasses 3D TVs, they were touting how you could watch it while lying on the couch, lying on your side.
You can watch it, but you won't see 3D. No.
Yes. That's interesting.
Yeah.
A little misleading, perhaps, in the advertising department there.
Yeah, wishful thinking.
Indeed. Okay, so you've got, as I recall, as I understand it, your system uses an optical system, basically something affixed to the front of the TV, of the flat panel TV, and then some electronics that are used to manipulate the actual pixels in the TV itself. Tell us a little bit more about how that system, how those two pieces work together.
Yeah, what we do is we have a lenticular or a slanted lenticular and other layers that are going under an angle over the screen. So from an angle from about approximately 10 degrees.
So there is a lenticular sort of a what I want to say, a groove structure in this optical piece, but it's at like a 10-degree angle from vertical.
Yes, and what that does is if you put the lenticular perfectly vertical, you only split resolution and views in the horizontal sense, where the pixels, the RGB components of the pixels, are also in that direction. So red, green, blue, red, green, blue. So if you then would move alongside these lenticular or striped optics, you would see red predominantly, then green, then blue. If you make it slanted, you can use subpixels, so red, green, and blue components from different pixels, not the one that is meant to be a pixel, but different subpixels to build a 3D pixel. And those don't need to be adjacent to each other. No, they even can form a triangle in the screen, which helps you with two things. You get better color reproduction in 3D, and also you don't only sacrifice horizontal resolution. If you have vertical slits or vertical lenticulars, you only sacrifice horizontal resolution. But if you have your lenticular slanted or at any angle other than vertical or horizontal, you can sacrifice a little vertical and a little horizontal resolution, which makes sure that the end image is better than by sacrificing one or the other, vertical or horizontal.
Right. That's actually a very good point. Because with passive glasses 3D TVs, as they are now from LG, Vizio, Toshiba, I think, you actually only get half resolution, and it turns out to be half vertical resolution, I believe, in each eye. So with a total pixel density of 1920 by 1080, each eye is seeing 1920 by 540.
Exactly. Yeah.
So some people even question whether or not to call that high def.
Yeah, yeah.
And so what you're saying is that your system treats sacrifices some horizontal and vertical resolution, but not as much in either direction.
Exactly. Yeah, that's true. We need resolution to make more partial images. In fact, I can reveal that we generate 26 partial images to be seen while looking at our screen. That would, if you used all the pixels one by one and in the without electronics or without optics, you would sacrifice 26 times the resolution. And that, you probably have seen our screen, is not the case. While we do it partially, we can restore most of that resolution again. And our screens are equipped with a 4K or a quad full HD LCD, from which we, as a result in 3D, still have more than full HD left when watching our Ultra D TVs.
Right. And this is another really important point to make, is that you are applying your system to Ultra HD TVs, which have 4 times the number of pixels as regular, quote unquote, high def TVs. And so when you're sacrificing a little bit of resolution in either direction, in both directions, you're still seeing a very high resolution image in each eye.
Yes, perception wise, because it's not easy to count the pixels anymore, because you can't identify a 3D pixel on the screen plane as you can with 2D pixels. But the perception is that it is a little higher than what we call in 2D full HD, full HD. Yeah.
But there's no way to quantify the actual resolution that each eye is seeing. Have I got that right? Is that what you're saying?
That's exactly what I'm saying. Yes, it's hard to do that, because there's no, you can't count the pixels. You can only say this looks similar than full HD, or it looks better than full HD, or something like that.
A subjective impression rather than an objective number.
Exactly, but the number is also not a very objective thing, because the number should then be related through this to the screen size. If you see full HD on a 100-inch TV, it's still a lousy resolution.
Particularly if you're sitting pretty close.
Yes, exactly.
Speaking of which, let me ask you this: is there an optimum range of distances that one should sit from an Ultra HD equipped TV? I assume there is.
Yes, now normally, or it used to be that once 3 times the diagonal was the optimal viewing distance for 2D TVs, and we
high definition.
High definition, yes. So if a television is 50-inch, you can sit at a distance of 150-inch.
Right.
Yeah, and we we optimized our 3D televisions to behave the same. So ours is also 3 times the diagonal. That's the optimal viewing distance.
Mm-hmm. Sound Pro 69 in the chat room is saying this also almost reminds me of some sound recording techniques, binaural sound recording techniques, in particular. Do you see any resemblance or similarity between recording binaurally and well, now recording binaural, capturing is one thing, but playing back is what you're really talking about.
Yeah. There is analogy, of course. It all relates to our total perception system, and the receivers of audio as well as visual are located on our head at a certain fixed distance.
Yeah.
If you, there is a variation, of course, in the different people, but still, it's pretty much the same for everyone. 65 millimeters eye distance and about 112 millimeters ear distance. So and you can make your capturing system as well as your reproduction system match as good as possible those distances, or optimize your viewing distance to your television to optimally have stereopsis or stereo audio.
Actually, just FYI to those of you who are listening, next week my guest is going to be, I'll make this announcement later too, my guest is going to be Brian McCarty, who does a lot of work with binaural recording. So just FYI, that'll be an interesting tie-in to this in a way.
Yeah.
Okay, so we talked about the optical layer or optical system, which is something that is bonded to the front of a TV, and it's permanent, I assume, right? You can't take it on and off.
No, you can't take it on and off. It's
right.
integrated with the front glass of the LC. Yeah.
Right. So we'll talk about that again in a minute, but I wanted to first talk about the electronics. The other part of this is that you have a particular digital signal processor that then manipulates the pixels. And I was fascinated to hear you talk about how you don't necessarily, the subpixels, the red, green, and blue subpixels are not necessarily confined to their corresponding full pixel, that you can in fact kind of cross the boundary from one full pixel to the other and use the subpixels almost independently. Have I got that right?
Yes, you've got that right. There is a limitation to that. There's a formula developed or found by a Dutch scientist. It's called the delta-nabla relation, because we base mostly our pixels on 3 colors, red, green, and blue. There are systems that have red, green, and white as well, but at the moment it mostly is red, green, and blue. And the ratio between the distances between red and blue, green and red, and blue and red, you have a triangle like this, and the ratio between the distances to my fingertips shouldn't be too different. So this setup is not okay. This setup is okay. So, and we use that by using the red and green parts of a 3D subpixel independently in space. We try to obey the law of good delta-nabla ratios, but we can still move them in 3D space independently based on the RGB triplets that we have available in the hardware pixels in the LC. And with our optics, we then can make a field of the 3 basic colors that generates a 3D picture in your perceptive system.
So you said as I recall, I've spoken to a number of the people from stream TV networks, and they were talking about how the red and blue subpixels were used differently than the green.
Yeah, there is a dependency in our eyes. We can better see green than red and blue. And if you see
we are most sensitive to green, correct?
Exactly. So what you do to the green pixel is more important for depth perception than what you do to the red and blue pixel. And we take that into account as well by moving the pixels around behind the optics. So no longer the 2D pixels are sorted in rows and columns, but the 3D pixels are built out of 3 components that can be anywhere over the screen and projected through our optics to a certain point in 3D.
Yeah, that is just mind-blowing to me, that you're basically taking all the subpixels on the screen and using them independently rather than as a triplet for each individual pixel. I mean, that is just super cool.
Yeah, and that means that we have to handle 12 times the amount of to the full HD screen in information, because we treat every pixel in sense as 3 pixels. We use a quad HD LCD to drive the thing, and 3 times quad HD is in fact 12 times HD, but then in color components.
That must take a tremendous amount of processing power, which I assume you can get now. I mean, processing power, as we know, increases as time goes on, and has been following Moore's law for quite a while now. So we are now at a point where we can relatively affordably have that kind of processing power, huh?
Yes, in the televisions that we produce at the moment, that part of the work is done by what we call an FPGA, a floating point graphics accelerator, a dedicated processing chip that is really equipped to drive pixels and subpixels. And we let that chip do the rendering, as we call it. So the driving of all the subpixels in the original LCD.
You know, that's interesting. I always thought FPGA stood for Field Programmable Gate Array, which
that's you're right. That's true.
Oh, okay. But it may very well use floating point arithmetic, which is fine. But it's a type of chip that basically you can load a program into it and have it do what you want. It's not necessarily a general purpose processor like the microprocessor in a computer or something, but it's programmable to do any specific task that you want. And I guess you're using those in this case to do this particular task.
Yeah, exactly. That's what we do.
Okay,
and
fantastic.
And we're working on a system which could work on an SoC, where the SoCs for phones and tablets are getting faster every day almost. In the end, we probably can use that. And most TVs are already equipped with some form of SoC. So we can try to piggyback on that.
Yeah. By the way, SoC, system on a chip. So it's basically the entire electronics, the entire processing that you want on a single chip. Which is what you need in order to get into small devices. Also, what you need to be able to produce lots of things inexpensively. So that's just by way of definition of that particular term. Okay, then the final piece of the puzzle is that the signal being delivered to the electronics needs to be in the Ultra D format, right?
Yes, and we achieved that by having what we called a C-Cube. Our company is called C-Cubic, and the main product on the electronic side is the C-Cube, which can convert stereo signal, so made for glasses-based 3D. It can convert that into autostereoscopic or Ultra D footage, but it also can take 2D and convert that into Ultra D, so that you can perceive 2D recordings or 2D shots for movies and video in 3D.
And again, the processing is fast enough to be able to do that in real time. How much lag is introduced in that process?
There is about a 4-frame lag, so 1/15 of a second if you have a 60 hertz screen.
Hmm. Okay, well, that's not
for live
too bad.
television. For our live television, that is pretty good because most of the time is lost in transmitting the signal. So if you watch a football match or anything else live, or nowadays the Winter Olympics, it reaches you seconds after that it's really happened.
So introducing another 15th of a second is no big deal.
No, that's what I argue. Yeah.
Yes, indeed. Okay. So you can accept an image from, say, a 3D Blu-ray player or a 3D broadcast or any 2D image, and in any case, the signal will be converted into the Ultra D format. What can you tell us about this Ultra D format? Is there any? I mean, I don't want to break any company secrets or anything, but what do the electronics and optical system need to be in that signal in order for it to do what it does?
We have to estimate or calculate from a stereo signal. We can partly calculate it. From a 2D signal, we have to estimate the depth of every pixel, or rather every subpixel, in respect to the screen. So we have to estimate where that pixel be if it was reality. And my nose would now stick out of the screen. That pixel should float in front of the screen. But the backdrop here, my map, should be somewhere in the screen, deep in the screen, because it's
behind the screen plane.
Exactly. And so for every subpixel, we try to estimate or calculate, and we can calculate it from a stereo signal. We can calculate it from our own type of recordings. There's time of flight cameras who can generate a depth value per pixel, and there's more of these devices. So we need depth per pixel.
Well, it's amazing that you're working with 4 times HD, so 8.8 million pixels times 3, so 25 million subpixels, and you're able to calculate the depth of each of them and send it along to the electronics with only a 4-frame delay. I mean, that's amazing to me.
Yes, it's quite an achievement. Our software and firmware department has worked very hard and came up with some very clever solutions to do that in the state-of-the-art hardware that we have available, of course.
And state-of-the-art algorithms as well.
Yes. One of the main guys that did algorithmic work for one of the big television companies now works for us. Yes.
Okay. Somebody in the chat room is asking, and I don't know the answer to this, I don't think so, are the Olympics being broadcast in 3D? They were 2 years ago in London, but I don't think they are this year. Have you heard anything about that?
No, I know that they're not.
Oh, okay. It was an experiment that 2 years ago that I guess didn't pan out too well.
No, I think that, sorry, I think that using glasses to watch these things like Olympics and other big sport events, which people tend to do with a group, is very annoying. Wearing glasses is annoying in the first place, but having to wear them to do something together is even
worse.
more annoying. So I think that 3D gets a real good second chance with other stereoscopic technologies such as ours.
Right. Well, certainly everybody I talk to about 3D just hates having to wear the glasses. So that's why I was really excited to have you on the show and tell us about this particular system, which I've seen a number of times. I've seen some demos, and it is really quite impressive. Now, before we get to when the general public might be able to see it, let me ask you this. You have this optical system, layer, film, whatever you want to call it, bonded to the front of the TV. You got the electronics in the TV. Is your intention that everything someone watches, be it from a 2D source or a 3D source, be viewed in 3D?
It's possible. With the solution that we offer, you can view everything in 3D. But we have a slider which you can operate from the remote control, with which you can set the amount of 3D that is generated by the system. So if you would like to see things in 2D for whatever reason, you can just put that slider to 0 and the image on the screen is 2D again. And you can also move the slider up to 200%, which obviously generates exaggerated 3D. But some people like the extra effect, certainly in advertising, where things really stick out of your screen and tend to come for a grasp right in front of your face. People can choose that by manipulating one slider in our system.
If someone said, I want to watch this particular thing in 2D, I don't want to have it be converted, and they set that slider to 0, what does the optical layer that's sitting there in front of the screen do to the image, if anything? I mean, I can't imagine it wouldn't distort it somehow. It's got lenticular grooves and so on in it. Does it cause any problems?
It caused any problems, big problems really, because it totally mixed up the 2D performance of the screen. But since we know how to steer all the subpixel information to be somewhere in space, we can also drive that to be somewhere in space on the screen plane. And
oh, of course.
And that then makes the screen suddenly 2D again.
Right. So you're compensating for the optical distortions that the optical layer naturally creates by essentially processing the image to have 0 depth, but still you're processing the image, taking that optical layer into effect.
Exactly. That's what we do.
I love it. That's great. Well, good. Then that addresses the concern that I know a lot of people will have, which is that they don't necessarily want to watch the nightly news in 3D or, something else. Casablanca, for example, some classic films, that purists certainly would not want to affect by having, an artificial 3D applied to them or so on. So you can turn it off and you won't experience that degradation.
No, or hardly.
No, hardly. Maybe slightly, but how much? The question is, are you willing to give up a tiny little bit of that in exchange for being able to see 3D when it's appropriate, at least without glasses, sharing it with your family and friends, and so on. This is the holy grail that a lot of people, including myself, have been hoping for. And so then the next question obviously is, when can I go to the store and buy one? And you're not going to be making TVs, right? You're selling or licensing this technology to television manufacturers, right?
Exactly. C-Cubic is an RDI company. It's a subsidiary of Stream TV, but we are the RDI company, as we call it, research, development, and industrialization. So what we do is we develop the technology, make prototypes based on that technology, and while making these prototypes, we try to design the machines that are necessary for mass production. And in fact, we have designed machines for that, and we're now talking to big Chinese TV manufacturers, so set makers, to have our machines and have our technology implemented in their products.
Can you tell us who?
Yes, I can name a few. That's Konka, Haier, BOE, Hisense. So that these are the 4 major brands in China.
Certainly. Any of the manufacturers from Japan that you've been working with and can tell us about?
We've been talking to Sharp and Toshiba. Toshiba, you would say, yeah.
In the States, I guess we would say Toshiba. And so you're talking with them, but maybe the negotiations aren't quite as far along as they are with the Chinese. When will we first see product in the stores in the U.S.?
This year.
This year.
Yeah.
From the Chinese companies, from Hisense and Konka and so on.
Yeah, Hisense is definitely available under a different brand in the States. Konka and Haier, I'm not sure. And the Japanese brands, obviously, Toshiba is certainly in the States as well.
Mm-hmm, mm-hmm.
And so in Europe.
Right. So we'll see TVs from some of these companies sometime this year in 2014.
I expect so, yes.
Mm. Mm. And will it carry much of a price premium? I mean, obviously that has to do with the set maker and the retailer and all that stuff. But how roughly, what kind of a price premium do you expect TVs with Ultra D to carry?
It's difficult to say because price is not only dependent on manufacturing costs or on cost of parts and transport. It's also how much is the public willing to pay for it.
Always the case, huh?
Yeah, and early adapters and people that really have money to spend will probably in the beginning be willing to pay a little more than in the end the mass will. So we think it should be in the environment of no more than 10-15% uplift in respect to a 2D TV.
Mm-hmm. Well, that wouldn't be too bad. Looking at my notes here, I do remember the few times that I've seen a demonstration, a couple times at CES, once here in Burbank where I live. As I walked around the screen, I still did see a slight bit of wavering, right? You're familiar with this, with a conventional lenticular screen, it's very pronounced. And with yours, it's much less, but it's still there a little bit. Is there, or at least it was in the last demo I saw. I'm sure the technology continues to improve. Will we ever see a situation where that simply doesn't appear at all?
It's difficult because part of the problem of having this waving is due to the way the video material or film is acquired. You only have a limited portion of the angle in which you can generate 3D. And I told you about the lenses of a stereo set that can be set further apart. So you have more 3D information. But if you take 2D, there is no way you can see the information behind me at the moment. I have to move away, and then you see it.
Then you can see it, yeah. Mm-hmm.
And I could remember that, and we do all sorts of developments based on that. But if it's not seen, we can show it. So there is a limitation in how far you can look around an object or anything in the scene. And for that not to lose the 3D, we repeat that over the total viewing angle of 120 degrees. So you will see this waving a little bit always, but we make sure that there is no pseudoscopic zone, so where you see cross-eyed. You go through a monoscopic zone if you go from one 3D area to another, and that is not as disturbing as it used to be with lenticular or barrier-based solutions.
At the moment, mostly the content that we can get for a UHD or Quad HD TV is still 1080p. It's still 1920 by 1080. Are you doing anything with the scaling up to UHD resolution, or are you allowing the TV to do that?
No, we use the scaling to drive all the pixels, of course, or in the end all the subpixels individually. But we do a normal upscale as is used in 2D televisions as well, to go from Full HD to Quad Full HD, Full HD, if there's no Quad Full HD material available, which is difficult in broadcast and on Blu-ray. You only can do that with the computer at the moment. Right.
Or in some cases streaming. Netflix has announced they're going to stream 4K, YouTube, Amazon Instant Video, I think, as well.
But then you use a computer, in fact, and the internet.
Yeah. Oh, yeah, exactly. Or a streaming box like a Roku or something like that.
Yeah.
As a little aside, since you're in Europe, let me ask you, what is the state of UHD in Europe? I know the EBU, the European Broadcast Union, is talking about it and working on standards. What's your sense of that? Have you got any inside scoop on how that's going in Europe?
I don't have a scoop. I hear that most of the broadcasters think it's too expensive to sacrifice much bandwidth to a standard 4K that is hardly being used through the televisions nowadays. They rely on television manufacturers to come up with better scaling algorithms or with information joined with the normal 2D signal to be able to more precisely scale up to 4K than really broadcasting 4K as a standard.
Almost like metadata on top of the 1920 by 1080 in order to, as you say, more effectively scale up.
Yeah, if you could send with every image the characteristics of an image. So, for instance, what's the real size of what you see in arc degrees or in meters, whatever? You could then calculate what the smallest detail would be that you need to see in such a situation. So you can calculate the needed resolution from the character and the size of the screen.
Got it. We've been talking about LCD TVs, which are really going to be the primary technology for Ultra HD TVs. But will the Ultra D technology that you've developed also work on other technologies such as OLED, which we've seen 4K or UHD OLEDs as well? We haven't really seen them on plasma, and plasma's on its way out anyway, so you probably aren't even thinking about plasma. But what about OLED?
OLED can definitely be used as a basis for the Ultra D technology, where with OLED you also have red, green, and blue subpixels, or even red, green, blue, and white subpixels. And we
in the
can
case
use
of LG,
that.
yeah.
You can even use that extra white pixel to gain resolution in the sense of real spatial resolution, but also in the resolution in color, of course, for which it is meant. We even are at the moment experimenting with LED-based, so not OLED, but LED-based video walls. So where the pixels are not lit by a LED backlight, but where, in which the pixels are RGB LEDs. And
right.
Also
so sort of like the giant jumbotrons in stadiums, and big giant displays, video walls, as you say, which have red, green, and blue LEDs that actually form the picture directly.
Exactly. That's what we are experimenting with. The first prototype will be, let's see, 6 feet high and 19 feet wide. So
wow,
will be quite impressive. Yeah.
That is very impressive.
Yeah, I hope to bring that to CES next year.
Next year, okay. Well, I'll certainly look forward to that.
Yeah.
And one of the reasons, I guess, that you can apply this to LED walls or OLEDs or whatever is that you're not depending upon polarization as everything, all other types of 3D are, which means that LCD TVs can be passive polarized glasses because they're polarized by nature. But plasmas, you have to use active glasses. You can't use polarization because they are not. The light coming out of them isn't polarized by nature. You could apply Ultra HD to a plasma if you wanted to, but as I said, you're probably not even thinking along those lines, are you?
No, we're not. No,
for one thing,
out.
Yeah, for one thing, it's on its way out. For another thing, it's difficult, if not impossible, to make a UHD plasma, except at a very, very large size. Panasonic did it with a 152-inch plasma, but that costs $500,000. So it's not going in my house anytime soon.
No, not in mine either.
Well, how are the studios responding to this? Have you been talking with the studios at all about perhaps encoding content with the Ultra HD format on their 3D content? Or is this not even important because you have this converter that will convert regular stereo?
We didn't want to depend on a new standard because that is always something that will go very slowly into the market, and adaptation will be a hassle because people will fight over how the standard should look like. And we know obviously that Dolby is trying to set a standard as well. So we are developing our own format, but we don't want to depend on that or on anyone else's format. So at the moment, we take 2D in, we take stereoscopic in any way or form in, and we'll probably also support all other formats that will arise, such as the Dolby format.
Well, that then brings me to this question, which is that Dolby, of course, is working on a stereo, glasses-free autostereoscopic system themselves called Dolby 3D. And if I'm not mistaken, I was led to believe that both your system and their system originated out of Philips research, and then the two of you took that initial research and went in different directions. Is that correct?
Almost.
Set me straight,
Yeah.
please.
Yeah, but no, both groups, most of the people that started those groups, and certainly mine, came from the development department within Philips that worked on autostereoscopic screens. Although Philips had been working on autostereoscopic since probably in the early 90s, one of the first patents was from 94, which is still a very good, valid patent. I only worked with Philips for 3 years, and so did most of my colleagues in C-Cubic. They worked for 3 to 5 years in Philips. So you can hardly say that everything came from Philips. So my background, as I told you, was holography. I've been active in virtual reality and computer-generated 3D for all of my life. So I tend to think that the Ultra D technology, at least, is partly independent from Philips.
Clearly so. I mean, you have taken that core or initial research and taken it to a whole nother level, and well beyond what they did. And it seems like in a somewhat different direction than Dolby. I've seen both systems, and they both look very good. But I must admit, I sure love the way yours looks, and I can't wait to get one in my house.
Me neither.
Well, that's so great. Thank you so much for being here. It's been a great discussion about glasses-free 3D and how C-Cubic and Stream TV Networks does it. All thanks to you, Walther Ruling, over in the Netherlands, staying up late for us. Thanks so much for being here.
Thank you, Scott. Bye-bye.
Bye now. Okay, so you can learn more about this at the C-Cubic website, ccubic.com. That's SEECUBIC.com. You can find me at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott, also at avsforum. You can also find previous episodes of Home Theater Geeks right here on twit.tv/HTG and on our YouTube channel, youtube.com/twit Home Theater Geeks. Next week, as I said during the show, my guest is going to be recording engineer Brian McCarty, who is deeply involved in the standards process with SMPTE, Society of Motion Picture and Television Engineers, and AES, the Audio Engineering Society. And we're going to be talking about audio systems for commercial cinema and in the home, what has gone before and what is coming up. So I hope you will join me for that. Until then, geek out.